Thank you very much. And thanks very much to the organizers for inviting me, and in particular for having this conference, which has been a lot of fun. I've been learning mathematics from Micah since long before I knew him, since I was a graduate student. My thesis was about, one of the things it was about was quasi-actions on trees. So, and one of the main inspirations was a paper by Micah with, and I've always called him Micah. I apologize. That was by him and Lee Mosher and Kevin White, and up to the present day. So this preprint right here, in some sense, you can think of it as directly inspired by a paper which was never published by. Did I drop something? Oh yeah, that's mine. Yeah. I probably want that. Thank you. Thank you. So yeah, a never published paper of Micah's with Lee Mosher. So this paper is about coning off boundaries of hyperbolic manifolds with totally geodesic boundary, which is important to what I'm talking about today. And of course, every once in a while I think about cubes as well. So okay, and today I'm going to talk about incubulable groups. So Pierre Emmanuel told us that cubes are everywhere. Almost true. But so here are I'm going to give some examples where we don't have cubes. But first I want to kind of, talk about a pretty general question. So I'll just write, I said it was general. Here's the question. So given some compact metrizable space, which is equal to the boundary of G for some hyperbolic G, so when is every hyperbolic group with boundary K cubulated? So what's an example of a positive answer, a space for which I have a positive answer? A circle, yeah, a circle is a good example. So an even simpler example would be a Cantor set, right? So, so what's funny about that? Okay. So it's simpler in the sense of lower dimensional, I guess. Okay, a circle, maybe the circle is the simplest, but I don't know. Okay, so a circle. So maybe this is the Cantor set. So if your boundary is either of these spaces, you're forced to be cubulated. If it's a Cantor set, it's because you're virtually free. And if it's a circle, the easiest way to see that is using the Segif construction. So I have a bunch of infinite order elements. Hyperbolic groups always have lots of infinite order loxodromic elements. And those give me codimension 1 subgroups of a group with circle boundary with which I can cubulate. So these are always cubulated. What about S2? So that's maybe the next simplest after S1. So this is of course open. Recent work of lots of people has shown that the answer to this question for S2 is related to other questions that we really want to know the answer to. It's equivalent to the Cannon conjecture. So maybe I'll just say this. So if I've got a hyperbolic group whose boundary is homeomorphic to S2, then G is cubulated if and only if G is Kleinian. Okay, after quotienting by a finite normal subgroup. Okay, if you just want to think about torsion-free groups, then it's just, I don't need to add any extra things here. And so this is due to, so in one direction, this is basically Kahn-Markovich together with a criterion of Bergeron and Wise. So. And in the other direction, there's a result of Peter Hasinski, building on earlier work of Vlad Markovich. Yes, I do mean the co-compactly cubulated here, though it's not actually that important. Yes?
Do we know that we have at least one co-dimension, one subgroup in that case, or not?
Not even that. Not even that, yeah. So if you could have one codimension, one subgroup, that would get you a long way towards where you want to be. Yeah, good question. All right, so I'm not going to answer this question today. So today I'm going to talk about something completely different. So today we're going to focus on a different boundary. So K equal to the Pontryagin sphere. Okay, and I'll write this as PS. And so there's a couple different ways you can think about the Pontryagin sphere. The maybe simplest way to describe it is to take a square carpet. So this is, okay, I should not get too lost drawing squares. And then, so I see a lot of squares, right? So, and so I can identify opposite sides to get, so identify this side with this side with this side, and then this side with this side, and this side with this side, and so on, and keep going, right? So you can think of this thing as kind of an infinite genus compact surface. Okay, obviously it's not a surface, and it's sort of far from a sphere, but one thing that it does have is if I take the, say the dimension of the second Czech cohomology is 1, and so it has a kind of, anything whose boundary is this will have a kind of fundamental class, but the first Czech cohomology is infinitely generated. All right, how do these arise? So these arise as boundaries at infinity of universal covers of pseudomanifolds, three-dimensional pseudomanifolds. So today, what am I going to mean by that? So today, so a three-dimensional pseudomanifold means the following. Well, it means M hat in the following. So first I'm going to let M be equal to a compact three-manifold with boundary. Let's say orientable. And then M hat is equal to a quotient space of M. And I can think of, if I want to write it as a kind of decomposition space, I can think of the set of N so that N is a boundary component. Okay, maybe I'll draw a picture. maybe I've got some boundary components. You can also describe it because three manifolds with boundary have, the boundary is kind of bicoloured. I could have also described this in a different way as I attach a cone to each boundary component. And I'm going ahead and drawing the picture just to make it clear that I mean a separate cone point for each boundary component. So if all the boundary components were spheres, I just get a manifold again, right? But if there is something higher genus, then maybe I get something different. Okay, so the theorem. Oh, sorry. Let me say a fact first. So fact, and this is maybe I'll write Swiatkowski's name here, but depending on. Okay, yeah. So this is basically due to Swiatkowski. So he proves something much more general, which is that if I have a nice enough metric on something that looks like m hat, this makes sense in any dimension, then the boundary at infinity of the universal cover will be a tree of manifolds, what he calls a tree of manifolds, and the Pontryagin sphere is a special case of that. So, if m hat admits a nice enough. Okay, I'm just gonna negatively curved metric. And I have the boundary, and I have G is equal to the fundamental group of m hat, which of course is just the fundamental group of M modulo the normal subgroup that contains all the boundary loops. So then has boundary of G equal to the boundary of the universal cover. So now this, whatever I mean by negatively curved metric, this thing should be at least cat 0, and it'll be cat minus 1 really. That this is homeomorphic to a Pontryagin sphere. Okay, so this gives you some way of building lots of groups with Pontryagin sphere boundary, and there are a lot of related constructions involving kind of right-angle Coxeter groups and so on that can get you a wide variety of QI types. But those things, if I'm using right-angle Coxeter groups and nothing else, are going to get me things that are cubulated. So we wanted to do something a little bit different, and so we come up with some examples which are not cubulable. So let's see. So there are many hyperbolic, so compact hyperbolic three manifolds with totally geodesic boundary so that call one of them M, so that M hat admits a cat minus 1 metric and or locally cat minus 1 metric. And if I take the fundamental group, that has to be a hyperbolic group, say it is not cubulable. And here, we don't just obstruct a co-compact action, we obstruct a proper action. So here, cubulable can mean, I was telling somebody at breakfast, 95% of the time when I say cubulable, I mean compactly cubulable. But today, I just mean a proper action. So maybe I'm going to make several remarks, but first, the first remark I want to make that there are geometric conditions that guarantee that M hat admits a locally capped -1 metric. So this actually comes from this other paper that the second archive number there, which is joint work with Colby-Callum. Okay, any questions about the statement?
No codimension 1 subgroup?
No, there are codimension 1 subgroups.
Is there a free action?
Is there a free action? Yeah. No, there's no, is there a free action?
So there's no proper action, there's a free action.
There will always be stabilizers, there will always be infinite stabilizers. Yeah. Yeah, any action will have infinite stabilizers. So, so let me make some remarks. And I wanted to say also, this is the thing that is connected to this 1997 paper, which was never published of Mikas, which is one of the two, well, anyway, one of several papers that has been important to me. Okay. So let me make some remarks. One is that these are three-dimensional examples, but they are closely related to some two-dimensional examples that I built with Henry Wilton and Alex Lubatsky a few years ago. So these k-fold triangle groups. So and they're, in fact, for certain of these groups, we find these finite index torsion-free subgroups, and those are embedded in these guys. So a second remark is that we get, when I say many, I'm actually not 100% sure what I mean by that. So here's something I can definitely say. Is we get infinitely many topological commensurability classes. Because we can make the genus of the singularities go to infinity, right? Now, as to whether the groups are abstractly commensurable to each other, we need to do something with round trees or something to figure that out, and we haven't figured that out yet. So maybe I'll just put it as a conjecture, is that there are infinitely many algebraically. Okay, so third remark. Oh, right. So Ian Agel pointed out to us that, and maybe I won't talk about this in any great detail, that the fact that these exist puts some restrictions on the possible relative cubulations of the manifolds M. So these things are virtually special by this Agel-Wise, this work. This maybe is already in Wise if they have boundary. Yes, it is already in Wise. So and you can show that, and they're relatively hyperbolic relative to these boundary surface groups. And so you can show that they have these sort of relative cubulations, these sort of, which were studied by Einstein and Groves. But they have to be somewhat restricted. The hyperplanes have to intersect the boundaries in infinite subgroups. So, and that's something, for example, that you don't need to do if you think about cusp hyperbolic manifolds. So maybe I'll just write relative cubulations of, not the coned off thing, but pi1 of m are restricted. Okay, and you can look at the paper if you want to learn more about that. Okay, let me say what the basic idea is. So the basic idea is I'm going to embed a subgroup that comes from this remark 1 that has property t. So the strategy is to embed an infinite group with property t in pi1 of m hat. So pi1 of m, of course, can contain no such subgroup, but we show that pi1 of m hat can. Okay, and so then maybe I need more space for the full strategy. Well, maybe not. Seems like there's more space now. So part 1 is, so we build certain 2 complexes. With property t pi1. And then part 2 is to put, embed in pseudomanifolds. Okay, and this is a kind of 4-stage process. So, so we truncate, thicken, reflect, and cone. Okay, and I'm going to say a bit more about those steps. And here's where I want to point out some recent very interesting work of Jankowitz and Shrivi. So that's very recent. So they kind of generalize some aspects of this procedure to kind of arbitrary dimensions and fit. So here I've got a 2 complex that I'm fitting inside a 3-dimensional pseudomanifold, and they build out of any d-dimensional complex a 2d minus 1-dimensional pseudomanifold that contains it as a pi1 injective subset. Okay, so they don't have quite all the geometry that we get, but they can do things like ensure asphericity and so on. And one of the things that I thought was interesting about the way they do things is they actually reverse the order of steps 3 and 4. So, maybe I want to write that like that. So they're doing in some settings. Anyway, it's a very cool paper. You should look at it. I'm realizing I probably have room for 3 boards here. So part 1, I'm not going to go into a huge amount of detail, but let me just say the following. So let's fix an integer k, which should be sufficiently large, So you should think k is 18. And anyway, so there's some, so e.g. So there are infinitely many k that work. I don't know exactly which k work, but let me tell you what's true for these k. So we're going to let theta be the one complex with 2 vertices and k edges, and no self loops, right? So, okay, I'm not going to draw 18, I'm going to draw 4. So in all my pictures, k is going to be 4, okay? Even though k is really secretly 18, okay? So, some deep work of Lubatsky, Phillips, and Sarnak implies that there's an infinite tower of regular covers of theta. So they're all regularly covering theta. That has some nice properties. And those properties are that, first, that the girth of these graphs is going to infinity. And second, for all n, the first non-trivial eigenvalue of the Laplacian is bigger than a half. If I normalize the Laplacian appropriately. I'm not going to tell you what that means. I'm going to tell you what it implies. Okay? So, so there's this criterion of Zhuk, which actually we use a formulation due to Bowman and Switkowski, I think. Yeah, Bowman and Switkowski again. Which says that if k is not a compactum now, k is a triangle complex, is a triangle complex, say compact, say finite. Triangle complex, and I should say aspherical, so that for all vertices, if I take this first eigenvalue of the Laplacian of the link, if that's bigger than a half, then the fundamental group of K has property T. And I just realized I also am not going to tell you what property T is. I'm going to tell you why I care about property T for the purposes of this talk, and that's because it's an obstruction to acting on cube complexes. If I have a group with property T, then result of Niblo and Reeves, and then in the infinite dimensional case by Cornulier, says that so if H has this property T, then any action on a cat zero cube complex has a global fixed point. Okay. Phew. So there's a lot of theorems that we're kind of chaining together here. Yeah, Mahan.
Yeah. So in the construction of this subgroup, are you going to construct something that's QI embedded?
Yes. Yes, it's going to be QI embedded. In fact, the manifold will retract, or not the manifold, the pseudo-manifold will actually retract to a subspace, which is whose fundamental group is this, is the property T group. Yeah?
Did you say you want lambda ones?
No. So lambda 1 is the first eigenvalue, first non-zero eigenvalue of the normalized Laplacian. It gives you some, so if lambda 1 is large, so then it means that the graph is an expander. So it's related to the Cheeger constant. So it tells you something about how easy it is to cut up a graph using a bunch of edges. Yeah, so maybe I'll just say that. So is a good expander. Okay. Other questions? Okay, so fine. This is something about graphs. I promised you 2 complexes and then 3 pseudomanifolds. So let's make the dimension a bit bigger. Okay, so T0 is going to be equal to a union of hexagons, so some of whose sides are green and some of whose sides are white. Okay, let me draw you a cartoon of what I'm doing.
Jason, how important is the color difference? It's very hard because the green and the white look the same.
The green and the white look the same. Okay. Okay, yeah, I'll make them bold.
Thank you.
Oh no. I have to draw 4 of them at once now. Okay, let me just draw kind of like that. Okay, so the idea is, so I've glued together, I've identified all the white edges, right? So I have actually I've got K hexagons here, but the green edges are left free, right? To form these 3 graphs that look like this theta graph that I started with over here, right? So let's call those theta 1, theta 2, and theta 3. All right, these are regular covers of this graph theta. This thing, by the way, this thing deformation retracts to sort of a wedge of circles. So deformation retracts to a graph. Its fundamental group is just free. And you can build a cover of it so that all the elevations of these theta I are isomorphic to gamma n. So maybe I'll say this is an exercise, or you can look at the paper, which says that for each n, there is a regular cover of T0 so that every elevation of any theta I is isomorphic as a graph to gamma n. Okay, so let's call this cover T sub n. Now, so I've got this cover. It's kind of hard to imagine. I have these enormous graphs, these enormous green graphs, right? It's made out of hexagons. Now, what happens if I cone off each green graph, right? I'm going to get a complex, a triangle complex, so that the link of every vertex is gamma n, right? And so by the Juk criterion, that's going to give me something whose fundamental group has property T, as long as it was aspherical, which I can ensure by making the girth at least 6, right? So, so if n is large enough so that the girth of gamma n is bigger than 6, really just bigger than or equal to 6, but bigger than 6 if I want something hyperbolic, so then the complex k sub n, which I can think of as kind of t sub n hat, has fundamental group hyperbolic with property T. Okay, so that's going to be the thing that for large n I want to stick inside of a hyperbolic three-dimensional pseudomanifold, or a negatively curved pseudomanifold. Okay. So that's the end of part 1, and I have 8 minutes to do part 2. T0 is, so T0 is filled in. Yeah, this is a 2 complex. Yeah, it's made out of hexagons. Thanks. Yeah, it's not just, it looks like just a graph, but it's filled in, yeah. Okay, so part 2. So what was the order I promised to do this in? Truncate, thicken, reflect. So I truncate it, so now I can take this, now go back to this thing Tn, it covers this T0, and T0 embeds in something, sorry, I'm going to use the colors a little bit, so into a handle body, which I can decorate in a certain way. So this is supposed to be just a thickened up copy of my Tn, or T0, right? So again, I'm drawing k equals 4. You should imagine k is 18. And so I can take this gadget, this handle body, and I can, so what I want to do is I want to reflect. So to reflect I need, so I've thickened it. Now I need to reflect. To reflect I need mirrors. So let me draw, so how do I choose mirrors? I can choose mirrors by drawing a trivalent graph on the boundary of this, handle body. So I'll do that. So this is just to give you kind of the idea. I mean, well, this is basically, if you extend this in the kind of obvious way over the entire boundary, so I've drawn blue trivalent graphs in each of the pairs of pants that forms part of the boundary. So part of the boundary of this handle body is these planar surfaces that correspond to the theta 1, theta 2, and theta 3. And the rest of it is these pairs of pants that I've cellulated in a particular way. And I've cellulated them by a trivalent graph because I want to think of these as mirrors, which are orthogonal to each other and orthogonal to the green faces, which come from the theta I. Okay, so fine. What do I want to say next? Oh, so you can show that this has a hyperbolic structure with those angles. So using Andreev's theorem. So using Andreev's theorem. What's that? I'm taking this embedding of T0 into Euclidean space. I'm just thickening it. And I claim that I can then divide up its boundary in a certain sort of natural way. Yeah.
You're building that guy. You're building the one just below T0.
Yeah. Oh, sorry. T0. This is meant to be a picture of T0 because it's the hexagon times k. And then I've glued the filled in hexagon times k. Yeah. That's the guy that I'm thickening up, yeah. Yeah. You can think, maybe it's helpful if I think that T0, this is homotopy equivalent to a sort of a complete bipartite graph, K3, K, right? So the each hexagon gives me one of the vertices of valence 3, and then the 3 edges give me these vertices of valence k. I don't know if that helps. Well, okay. Okay, maybe that's not so helpful. Anyway, so anyway, just to clarify, and so this I can think of also as a thickening of that graph sitting inside R3. So this has a lot of symmetries. So there's like a D3 times dk symmetry group, and it sort of quotients down to a certain pentagonal prism with certain angles on it. So there's like a pi over k angle here, and there's a pi over 4 angle here, and a pi over 4 angle here, and where does the 3 go? The 3 goes here. Okay, where the green stuff is this right here. If I want to think about, for example, the octagon, that goes to this face right here, and so on. Okay, so this if I let k really be anything, I think, but certainly for k equals 18, this is going to satisfy the hypotheses of Andreev's theorem, and we can that means that I can hyperbolize this gadget, right? So I get this polyhedron, which is a natural kind of quotient of this thing. I make it a hyperbolic polyhedron, and that gives me a hyperbolic structure here where all the neighboring faces make right angles with each other. Okay, so hyperbolize this H0, which I forgot to name, so this is H0 with right angles. Okay, okay, I only have a minute. Maybe what I'll just say is that okay, I'll write something briefly over here. So I have this cover, so I've got T0, and it's being covered by this Tn. This is embeds by a topological homotopy equivalence into this H0. There's a corresponding cover by this Hn, and now I want to take this and I want to make it an orbifold by adding mirrors to all the non-green faces. I'm sorry, if you can't see green, that means the faces that don't have anything to do with the theta graphs. So we can mirror the non-peripheral faces to make an orbifold. And so now what I can do is I can take a certain, now I can make a manifold cover. So this is meant to be a manifold. And this is an orbifold cover. If I do this very carefully, I can ensure, well, first of all, I want to do this in a way so that this topologically, I can embed the Hn back up in M. And if I do this carefully enough, I can ensure that the injectivity radius of the boundary of M is large. So we want one, the injectivity radius of the boundary VAM to be huge. And two, if I call this lift, let's call this phi, we want phi of h should have a big buffer. Okay. Now, whatever these are the input to my paper with Colby, which I think, yeah, so, which is the second paper up there, which are going to get us that m hat is negatively curved, and hn hat, pi 1 embeds. Okay. And that's, and that gets you what you want, because pi 1 of hn hat, if I just think of it as the ordinary fundamental group, is the fundamental group of this kn, which has property t. Okay, that's it. Thank you.
Any questions for Jason? I'm sorry, go ahead, you birthday boy.
So that, but the M hat itself, you know about it having properties or anything like that?
No, no. So it definitely does not. So the question was,